Hello, this is Abhishek Dangal, roll number 21NS0243 from Namsi Government College, third semester. I am here to give short presentation about the topic LCR circuit. Now let us move forward. Firstly, discussing about what is LCR circuit. Any electronic LCR circuit contains a resistor of R ohms, a capacitor of C farad, and an inductor of L Henry, all connected in a series combination with each other. Since all the three elements of the LCR circuit are connected in series, the current passing through each of them is the same and is equivalent to the total current I passing through the circuit. Since a circuit that contains L, R, and C components at some particular frequency can make the L and C or some of their electrical effects disappear completely. Now, let us look at a brief explanation of LCR circuit. The LCR circuit can act as just a capacitor, just a resistor, or just an inductor individually. The LCR circuit is also used to enhance the voltage to increase the voltage passing through the individual components of the circuit. This voltage can be much larger than the external voltage applied to the circuit. LCR circuits are also useful to change the impedance of the circuit to increase or decrease the resistance to the current of an different frequencies. All these effects either be used separately or can be used all together to get the desired results in electronic devices. This is our LCR circuit diagram, and this diagram consists of all the components of the module such as inductance L, capacitance C, and resistance R. It fulfills along with its properties like reactance, impedance, and phase. This module discusses the overall effect of L, C, and R when connected in series and supplied by an alternating voltage. In such arrangements, the current provided passes through all the elements of the circuit equally. VR, VC, VL symbolize the amount of individual voltage across the resistor, capacitor, and inductor respectively. The three components of an LCR circuit works together to produce different effects. First one is resistor. The resistor limits the current flow. It helps in controlling the power or voltage that is applied to the LCR circuit. The resistor is a component in an electronic device that limits the flow of electric current. The resistor helps controls the amount of power or voltage that is applied to the LCR circuit. This is important because it prevents too much current from flowing through the other components in the circuit. Now let us see the work of capacitor. A capacitor stores energy and releases it in a controlled manner. It helps in controlling the voltage or power that is applied to the LCR circuit. The capacitor stores energy and releases it in a controlled manner, prevents too much current through the L resistor. Now lastly, we'll discuss about inductor. An inductor resists change in current flow. It helps in controlling the fluctuations in current flow. The inductor resists change in current flow, which helps to stabilize the LCR circuit. The LCR circuit is used as a part of electronic device such as cell phones, televisions, and computers to regulate the intensity of light emitted from the devices. Here we can see that this is our LCR circuit diagram, and here this L is our inductance. You see the inductance. This C is our capacitor, and this is R, and this R is our resistor. This minus L di by dt describes total induced EMF produced by inductance, or this minus L di by dt describes total amount of induced over C is our total voltage, total this I is our instantaneous alternating current, and this E is our EMF of LCR circuit. And now let us consider I is equals to total current flow in LCR circuit, um, and we already know L is equals to inductance, C is equals to capacitance. Now we can tell that total EMF in the loop equals to potential difference across capacitor and potential difference across R. What I am telling is total EMF. What is total EMF across the circuit is nothing but the total potential difference across capacitor, that is this one, and the across potential difference across resistor. So we can write total EMF in loop equals to potential difference across capacitor plus potential difference across R, or we can write E plus minus L di by dt equals to Q over C plus IR. This is from our this is or E equals to L di over dt plus Q over C plus IR. Let us take this as equation number 1. Now we have to clear our target. What is our target? Our target is to find out the EMF of LCR circuit and phase angle phi. Now our target is to find out number 1 is the EMF of LCR circuit. Here our number 1 target is to find the EMF of our LCR circuit, and number 2 target is to find phase angle phi. Now we take equation number 1, that is our E equals to L di over dt plus q by c plus ir. From this equation, we will eventually find the value of E as E equals to I naught whole R sin omega t plus L omega minus 1 over omega c whole cos omega t. This is the value of E that we found by taking equation number 1 and a little bit of calculation under equation 1. Now let me take this equation as equation number 2, and also we'll find impedance of our circuit as Z, that will be equals to root over R square plus L omega minus 1 by omega into C whole square. We can write this as equation number 3. From this equation number 2 and 3, from equation 2 and 3, we will again get the value of E, that will be equal to we will get the value of E that will be equals to I naught Z R by Z sin omega t plus L omega minus 1 by omega c whole z into cos omega t. We can write this as equation number 8. And now we suppose this value R over Z and this value L omega minus 1 by omega c over Z as cos theta and sin theta respectively. So now we write R over Z equals to cos theta and L omega minus 1 by omega c over Z equals to sin theta. And by substituting these values in equation number 8, we will find the value of theta, which is exactly our second aim, that is phase angle theta, as I'll write. We will find after substituting the value of Rz equals to cos theta and this value in equation number 8, we will find theta equals to tan inverse whole L omega minus 1 by omega c over R. This is our phase angle. And this is exactly our second aim to find. This is our phase angle. Earlier we considered this as phi, but this is nothing but this phi is equals to theta. If we plot a graph of EMF versus current with respect to phase angle theta or phi, whatever you can say, like this one. If we plotted the graph, impedance versus current with respect to theta, phase angle, we will find the graph as this. Theta is our phase angle. This is very important one. Now from equation number 8, and what is our equation number 8? Equation number 8 is nothing but it is the equals to I naught z r by z sine omega t plus L omega minus 1 over omega c by z cos omega t. Equation number 8, and a little bit of calculation involving in this equation number 8, you will get, will again the per exact value of our EMF, and that will be E equals to E naught sine omega t plus theta. This is our first target. What we was finding till now, our two targets had been fulfilled. That is target number 1, which was our to find EMF of our LCR circuit, which we find as equals to E naught sine omega t plus theta whole, and our number 2 target was to find phase angle, that is phi or theta, and we had find that one as tan inverse L omega minus 1 by omega c over r. At the end of our calculation, after when we find phase angle, that is our theta is equals to tan inverse whole L omega minus 1 by omega c over r whole. There arises three cases in front of us. In front of us, there arises three cases. First one is that is our case 1, when omega c is greater than 1 by omega c. This means that inductive reactance is greater than capacitive reactance. This means when INDUCTI, inductive reactance is greater than capacitive reactance. And another case arises, and that is case number 2, when omega c is less than 1 over omega c, and case number 3 is our omega c is equals to 1 over and that is this is omega L. Oh, sorry. This is omega L, and this is also omega L, and this is also omega L. When omega L is equals to omega C, I will show the phasor diagram for each cases, and also show what will happen in each cases. We can see here the phasor diagrams that are drawn for the following possible cases that we had already discussed little about. And for case number 1, when W that is our omega L is greater than 1 over omega C, that is inductive reactance is greater than capacitive reactance, then we will find omega L minus 1 by omega C is positive, and tan theta is also positive, or theta is positive. We can see here is in case 1 when omega L is greater than 1 over omega C. This is the phasor diagram for first case. The circuit behaves as inductive circuit, and the current lags the voltage by phase angle theta. The phasor diagram is given as this. We can see this is the phasor diagram for case number 1 when omega L is greater than 1 over omega C. We can see here the circuit behave as inductive circuit, and the current lags the voltage by phase angle theta. This will happen for the first case, and for the second case when omega L is less than 1 over omega C, then omega L minus omega C will be negative, and also theta will be negative. Circuit will behave as capacitive circuit. This means current leads the voltage by a phase angle theta. The corresponding phasor diagram is given by this one. We can see here this is the phasor diagram for second case, and here current leads the voltage by phase angle theta. Current leads the voltage by a phase angle theta. In the first cases, that is when the circuit behaves as inductive circuit and the current lags the voltage by phase angle theta, and this is exactly opposite, that is the current leads the voltage by a phase angle theta. And for the last third case, and that is our case number 3, when omega L is equals to 1 over omega C, then what will happen is current and voltage are in phase, and the our this Z will give us the impedance of the circuit. This is the phasor diagram for the last case, that is our case number 3.